Hi there, welcome to lecture 12 of Fox. This is our second lecture on graphs, and we're going to be talking about matching and coloring, two very important tasks on graphs. And we'll even cover an application to optimal stable dating, so stay tuned, lots of excitement. Okay, but as usual, let's have a quick recap of what we did last lecture. So we talked about graphs, we introduced graphs, equivalent graphs, i.e. isomorphism, we talked about connectivity, paths, degrees, common graphs, and the all-important handshaking theorem, which says that if you take any graph, okay, and we're talking about undirected simple graphs technically. So if you take any graph and you add up the degrees of each vertex, that equals twice the number of edges. Okay, that's a very fundamental result. Then we talked, brief overview of different kinds of graphs, trees, planar graphs, multi-graphs, weighted graphs, directed graphs, lots of different kinds of graphs for all the various types of applications that we might, like to apply graphs to. Anytime you have different kinds of relationships. Okay. And lastly, we touched on this very important task of a computer scientist, or this very important skill of a computer scientist, which is to take a problem in some random domain and be able to massage it so that, it can be phrased as a graph problem. So you can use all the tools and algorithms and theorems of graph theory to solve the problem. Okay, now what are we going to talk about today? Okay, so today we're going to talk about matching, in particular bipartite matching. So we're going to introduce this concept of the bipartite graph. We already saw the complete bipartite graph. Okay, and we'll see some applications to the optimal sort of stable dating, the mathematics of dating. I'll show you how to optimally date. Okay. Then we'll talk about another graph algorithm which is called coloring, and that's relevant to conflict graphs, which we talked about some time ago. Okay, and finally I'll just give you a whirlwind tour of several different kinds of graph problems, some of which are easy, i.e. we know how to solve them efficiently today, and some of which are hard, i.e. we don't know how to solve them efficiently today. So if you want to become famous, solve one of these hard problems. Okay, and as usual, let's head off to the board and talk about matching. Okay, so we're going to start with a motivating, contentious example, and I already drew it on the board for you. Sex in America. So that's like a headline title, right? Everyone's interested in sex in America. Okay, now suppose we're interested in just the opposite sex relationships. So here I've got a bunch of men, actually 10 men, and here I've got a bunch of women in red, 10 women, and we're interested in the opposite sex relationships. And so, I've drawn in blue the links which are partner, this man has had 3 partners, 1, 2, 3. So that's what these links. So the relationship was a partner of. Okay, sometime in their life, presumably at different times if you've had more than one partner. Okay, and so we can go and do a survey, right? We can ask this person, how many partners do you have? 2. How many? 1, 2, 1, and so on. And we can do the same thing to the women. How many partners? 3. Partners? 1, 1, 3, 1, and so on. Okay, and so this survey has been done many times, and the one I'm going to be referring to is the one in this very thick book called The Social Organization of Sexuality, and they came out with a survey and a conclusion, and that made the headlines. And so I'm going to summarize this thick book for you, or at least the part that we're going to be interested in. Okay, so when they did this survey, they found that and this is what made the headlines. The men had men have on average 74% more partners than women. Okay, interesting. What's behaviorally going on here? What's up with these men, these promiscuous men? Okay, but anyway, so let's continue the story. So, now that one headline comes out, you can't stop this flood of headlines. So ABC News. So let's call it SOS. The Social Organization of Sexuality. ABC Nightly News came out with their own survey, and groundbreaking survey. Groundbreaking. Going where few scientific surveys have gone before. Going where few have gone before. Okay? This is not me saying it. They said this. We're going to present you the results of this groundbreaking where few have gone before. Okay. And what did they say? They said that men have, on average, 20 partners, and women have 6. So 33% more for men. Okay. Wow. Okay. And, once ABC comes out with something, well, the New York Times is going to come out with something.
Okay, and what did they say? They said that men, on average, have 7 partners, and women have, I believe it was 4. Yes, 4. So 75% more for men. Okay, so now let me make my points. Okay, so the first point is, which do you believe? Okay. Which do you believe? Okay. And we might sit down and think about this and say, well, at least these 2 surveys agree, so maybe these guys have gone off the deep end here and done something strange. I don't trust this 233% number. These guys say 74%, 75%, so it's probably around that. Okay, and maybe some people do this, but the first thing that, but even whichever you believe, you're going to end up with the conclusion that, men have way more. Okay, and then the second question is, what? Aren't we mathematicians? We're studying mathematics. These are real-world issues, real-world contentious issues. Leave it to the real-world people. We are mathematicians. And I come into this and say, no. Okay. And it's exactly when you're dealing with contentious issues that things have a tendency to make headlines and emotions tend to flare. And sometimes, for such issues, it can be much better to just have some, hard, cold reasoning, something like a theorem that you cannot debate the truth of, that you can take to the bank and settle such contentious issues so that emotions do not flare, so that media cannot, just wildly say things. Okay, and here's a problem. Media wildly says things, and when they put numbers in here, you get the impression, you get the feeling that, it must be more credible. Okay? And sometimes people use numbers to scare other people into thinking, don't debate me, I've got numbers on my side. When they show you numbers and it's dealing with a contentious issue, that's when you need to dig deep. Okay, so we're going to dig deep, and we're going to see that graphs are relevant. Okay, I've already shown you that graphs are relevant, and we're going to try to understand what's going on here. But the point is that just because an issue is contentious, you don't get to avoid the truth. And truth for us is going to be a theorem. You can take it to the bank. Okay, so let's try to see, what's sort of the ideal world that we might have been expecting. So the ideal world we might have been expecting is 5, 6, 7, 8, 9, 10 boys, and here and 10 girls. 1, 2, 3, 4, 5, 6, 9, 10. And maybe the ideal world we were expecting is that everyone is kind of monogamously partnered with one other person, and that's it. Partners for life, and you're done. Okay? So everyone has one partner, and vice versa, and this is kind of the ideal world. Okay? Or maybe it's for some people the ideal world. And what it seems like this media is trying to portray is, something like the following, strange world, where, where let's say one dude is servicing all the women, something like this. Okay, maybe 2. I don't know what's going on. I don't know what the media is trying to portray, but here are 2 sort of extreme worlds. Okay, now let's analyze. Let's tinker a little. Okay, so when you ask people to report their number of opposite sex relationships, these guys report 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And these guys report 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And when you take the average, you're going to get 1 here, and you're going to get 1 here. Okay, and as we expected in this quote-unquote ideal world. Okay. Now when you ask these guys to report, this guy's going to report 10, 0, 0, 0, 0, 0, 0, 0, 0, 10. Okay. Imagine that there are 10 people on each side here. Okay, and then when you take the average, well, what's the average? This is the interesting one, because the average is the total divided by the number of people, and the total here is 20, and you divide by the number of people, which is 10, you get 20 divided by 10, you get an average of 2. Okay. So let's see how the women report. The women report 2, 2, 2, 2, 2, 2, 2, 2, 2. Well, the average here is very easy to compute. Everyone's reporting 2, so the average is 2. Okay, so then clearly this is not the world that the media is trying to portray with numbers and credibility and all that stuff. So maybe it's this world. So I encourage you to go for this world and compute the average for men and the average for women. I don't need to compute it because I already know a theorem. And I have a theorem that says that these will be equal. These two averages will be equal. Okay, and okay, I've simplified a little bit, right? I've simplified in the sense that I've assumed that the number of men and the number of women are equal. We can deal with that. I've also simplified and only considered the opposite sex partnerships. Okay, and we can even deal with that. Again, you can look in the exercises in the book which deal with that. Okay. But we'll just prove the fundamental basic theorem that says that the average number for men must equal the average number for women. Equal! And okay, if you deal with the fact that there are slightly more women in the US and slightly less men, well, then the averages can deviate a little bit, but by not more than about 1%. So where is this 74% number coming from? And where is this 233% number coming from? So, let's address that, but let's first prove. Okay. The theorem, and I'm going to put it in a box because it's a contentious issue, so we'll call it a contentious theorem. Okay. Theorem. If number of men equals number of women, then average for men is equal to average for women. Period. Or exclamation point. And there's nothing else we can do. Okay, that's a theorem. Okay, so let's prove it. Okay, so, we have to think about how did we get the average. We take all the numbers reported, add them up, and divide by the number of men. Okay, so the number reported is exactly the degree. Okay, it's the degree of the men. Now let's call the number of relationships, let's call that E. It's the number of links in this graph. Okay, so if you look at this, if you add up the degrees, so each edge, each link contributes 1 to a degree of a man and 1 to a degree of a woman. So if you add up the number of edges, you must get the sum of the degrees. And here, let's look, there are 20 edges and the sum of the degrees is 20. Here you have 10 edges and the sum of the degrees is 10. Okay, so proof. Okay, the number of edges, E, is exactly equal to the sum of the number of partners, the sum of the degrees, for men. Okay. But it's also equal to the sum of the degrees for women. So E equals sum, and I will put that a little bit lower, E equals the sum of degrees for women. Okay. But the average degree, or the average number of partners equals sum divided by number. Okay, so the average for number of partners for men equals the sum over number of men equals E divided by the number of men. And the average number of partners for women equals the sum of the degrees divided by number of women, which is equal to E divided by number of women. Now, if the number of men equals the number of women, then this is E divided by number of men, which equals E divided by number of women. End of proof. Theorem proved. Okay, so these two are equal. Now, if we want to generalize to, let's say, the US, where there are slightly more women and slightly less men, you'll see that this number will become slightly lower and this number will become slightly larger. As there are approximately 1%, maybe, or 0.5% more women, the difference between these two ratios will be approximately 1%, not more than 1%. Where is this 74% coming from? Where is this 233% coming from? 75%? Well, now, you decide. Do you want to believe a theorem which says that these average number of partners for men and women has to be basically the same? Or do you want to believe the news media? Me? I go with the theorem. You can take the theorem to the bank. Okay, now, I want to read for you what happened in this book, in the paragraph, just the one paragraph after this was reported. Because I was curious. I said, what the hell? these guys said this and that was it. No, the scientists came back and said in the next paragraph. Okay, now there is a basic adding up constraint that these gender differences seem to violate. What's the basic adding up constraint? That the sum of the relationships for men must equal the sum of the relationships for women. Okay. And once you agree on that, then you have, the sum divided by number of men, sum divided by number of women. Since these are approximately the same, those two average number of partners must be the same. And they realized it and they said it in the next paragraph. Okay. Logically, men should have the same number of female sex partners as women have male sex partners. We note that this inconsistency has been found as well, in other surveys in recent years in the United States, in the United Kingdom, in France, in Finland, and elsewhere. Okay, so people are finding this inconsistency everywhere, and they know it's an inconsistency, but the news media didn't report that. And they even go on to say, this inconsistency constitutes an important puzzle for which we, i.e. the authors, like others, have no good answer. So why doesn't the media say, men have 74% partners, they're more partners than women, but by the way, something must be wrong with our data because, that's not possible. That's not going to make headlines. Okay. And now, lots of people can conjecture as to why the data shows this and what's going on. Maybe men overreport, women underreport, who knows? Okay. But the point is that if you're a national news media outlet, you have a responsibility to, at least do basic math and figure out that this cannot be right. Or at least read the next paragraph from the book you're quoting. This is why contentious issues, numbers involved, people saying, believe me, don't believe them. Dig deeper, check. Math, theorem, take it to the bank. Okay, now, we're actually going to study matching, in a sort of a more general setting. Okay, and whenever we talk about matching, we talk about what are called bipartite graphs. Okay, so this is an example of a bipartite graph because there are two types of nodes, the blue and the red. Okay, and all the edges, all the relationships go from one type to the other, so from blue to red. Okay, and this is an even more special scenario in which we have matched all the blue to the red. Okay, and that's a very important general task, matching. Okay. So you observe that, there's a 1-for-1 matching. Every blue has a red and vice versa. And that's why we call this a matching. In fact, we call this a complete matching because all the blue nodes are matched and all the red nodes are matched. Okay. So we're going to study matching. Okay, with this motivational example to say that, matching is so important it's even made the headlines. Okay, let's do a speedy race and we'll be back. Wow. Whoa! Okay, so let's talk about bipartite matching. Okay. And, the general setting is you have these, so a bipartite graph has these two types of nodes, these two types of vertices, and for convenience we'll call them the blue and the red, or the left and the right. Okay. And all the edges go from the left to the right. Okay. So, let me show you an example. Okay. And we'll move to a new application. So, resource allocation. So you have tasks. So I'll call the tasks in blue. You have 4 tasks, and the resources that you can use to do these tasks, I'll put them in red. Okay, so you have tasks and resources. Let's say you have 5 resources. Okay, and so let me call the tasks T1, T2, T3, T4, and let's call the resources R1, R2, R3, R4, R5. Okay, and now I'm gonna introduce the relationships between tasks and resources. Okay, and so basically, each task can be done by some subset of the resources. So, for example, this task 1 can be done by resource 1, 4, or 5. Okay, and task 2 can be done by resource 3 or 5. Okay, and task 3 can be done by resource 1 or 4. And task 4 can be done by 2, 3, or 5. 2, 3, or 5. Okay, so the way this graph can be read is that, this task, so the links, task 1 can be done by resources 1, 4, and 5. Now the goal is to assign tasks to resources, but you have to assign all the tasks, and you cannot use a resource more than once. Okay, so we're asking for a matching that what's called saturates or a complete matching, a matching that saturates the left vertices. So whichever vertices typically that you want to saturate, we put them on the left. Okay? So can we find a matching? So can we find a matching? Okay, so match tasks to resources. Match tasks to resources. Now the idea here is, okay, so let's see if we can do it. And in this particular case, we can. So for example, we can use resource 4 to do task 1. Okay, resource 4 to do task 1. So I'm going to assign task 1 to resource 4. How shall I draw that? Well, let's say I'll draw a red line here. Thick red line. Okay. And now that we have assigned resource 4 to task 1, look, task 3 also needs to use resource 4, but that's now used up. So we can assign task 3 to resource 1. Okay. So here's another thick line. Okay. And now let's do task 4 and 2. So task 2 can use, for example, resource, let's say resource 5 if we wanted to, or let's say resource 3. Okay, and then task 4 has available 2 or 5, so let's say we go with resource 5. Okay. So, how do we represent? Okay, so now we don't usually draw things like this. How do we represent this matching? As a solution on a computer, we would just say T1 is matched to R1. So T1 R1, T2 R3, T2 R3, T3 R1. T1 is matched to R4. T3 is matched to R1, and T4 to R5. Now you will observe, so we say that this is a complete left matching because every task is matched. Every task has a corresponding resource. No resource is used more than once, okay? But not all resources may get used. Okay. Let's do one more example. Okay. Another example. Similar setup. Okay, so 4 tasks. T1, T2, T3, T4. Okay, and you have resources R1, R2, R3, R4, R5. And now let me show you for this example which resources can do which tasks. Okay, so 1 can be done on 1, 3, 4, and 5. So many ways to do task 1. Okay, task 2 can be done on resource 3 and 4. Task 3 can be done on resource 3 and 4. Task 4 can be done on resources 3 and 4. Okay. So there, I've assigned tasks. I mean, I've told you which tasks can be done by which resources, and now pause the video and, solve the same problem. Okay. Solve the problem. Figure out which tasks to assign to which resources so that every task can be done and you don't use resources more than once. And that means that you construct a matching. A matching technically is just a collection of edges. See, these are all edges where, no 2 edges share the same vertices. Okay. And if you pause the video and are coming back and you failed to find such a matching, I would normally say you're such a bad finder of matchings, but if you failed, you actually tried to do the right thing and failed because it cannot be done. And now let me give you a proof that it cannot be done. Okay. So my proof is very simple. I'm going to look at T2, T3, and T4. So I'm going to look at these guys. Okay. And I'm going to observe that, if you look at T2, T3, and T4, as a collection of 3 vertices, we can look at where do all their edges go. And all their edges go to these two vertices, R3 and R4. Okay? And one nice convenient way of referring to this is we say that the neighborhood of T2, 3, and 4 is R3, R4. So all edges from T2, T3, and T4 go to R3, R4. Okay? So we say that the neighborhood of the set of vertices T2, T3, T4 is exactly the set of vertices R3, R4. And you can talk about the neighborhood of one vertex, you can talk about the neighborhood of a set. So the neighborhood of T1 is R1, R3, R4, R5. The neighborhood of T2 is R3, R4. So the neighborhood for just a single vertex is just who am I connected to? Who are my neighbors in this graph? Okay. And if you think about it, a little bit, you will say, well, so this just means that all the edges from here go to here. So now if I'm going to match these guys can only be matched to the corresponding neighbors of that set. And if there are only two members in this set, well, then how am I going to match all three of those unless I'm allowed to reuse a resource? So that is exactly the proof that it cannot be done. Okay? There are more tasks than resources that can do those tasks. There are more tasks than resources that can do those tasks. Okay. So if we call this set X, okay, so we have a set X is equal to T1, T2, T3, T2, T3, T2, T3, T4. If this is a set X, okay, then the neighborhood of X is equal to R3, R4, and the size of the neighborhood of X is less than the size of X, and so that means it cannot be done. In some sense, you can think of X as being a witness, as being a subset that can immediately prove to you that you cannot do it. Okay. So this subset proves that there is no matching. We call this subset a left subset, and we call this the neighborhood of that left subset, which happens to be a right subset of the vertices. And so, immediately we see that if there's going to be a matching, this condition cannot happen for any left subset. So for any left subset X, it must be that the size of X is less equal to the size of the neighborhood. Because if that's not the case, you just don't have enough for that particular subset. You just don't have enough resources, to spread around, to go around. Okay? Because all those, if in this scenario, all these resources, all these neighbors have to be spread among more, customers, and that's not possible. Okay? This is called Hall's condition. Okay. And what Hall proved, and you can see the proof in the text, it's proved by strong induction. What Hall proved, okay, so this is just a way to, so if this is necessary, if you violate this condition, there is no way to perform the matching. There's no way to allocate the resources to tasks. Now you might wonder, if you satisfy this condition for all subsets, does that mean that there must be a way to perform the matching? And what Hall proved is yes, by strong induction. Hall proved that if this condition, if Hall's condition holds, then there is always a way to match the left completely with right vertices. And that's called Hall's theorem. Now, okay, so let's check, for example, here where we were able to do it. Well, let's look at the neighborhood of, for example, T1, T2. T1, T2. Well, T1 has neighbors R1, R4, R5. So the neighborhood of T1, T2 is R1, R4, R5, R3 is R1, R3, R4, R5. And you see that the size of the neighborhood is at least as large as the size of the original left set. And what Hall's theorem says is that if that's true for any subset on the left, then you have to be able to find a matching. And it can be proved. It's something you can take to the bank. Now, and it's proved in the text by strong induction. So we won't go through the proof. If you're interested, look in the book. Okay. So what we have to do in order to make sure that there is a matching from the left tasks to the right resources is to verify Hall's condition for all subsets on the left. And if it's verified for all subsets on the left, you know there's a matching. Well, the number of subsets on the left is a large number of subsets, so it's hard to verify. So it turns out that almost as useful is a much simpler sort of version of this. Okay, it follows immediately from Hall's condition. If Hall's condition is true, you know there's a matching. There's a much simpler version of this, which we will prove, and that's usually the more useful one. Okay, basically what it says is that, now this is not, so basically what it says is that, when you look at your vertices on the left, so you have your left vertices, and you have your right vertices. Quick question. Can there be fewer right vertices than left if you want a complete matching? Pause 1, 2, answer. If you said no, then you're right, because the subset of all the left vertices will violate Hall's condition. So there have to be at least as many right vertices. Okay. Now, you can look, okay, so now you add some, you add some links, okay, and you want to know, is there guaranteed to be a matching? Okay. A way to assign all the blue to unique reds, okay, such along edges. Okay. And so what you can do is you can look at the minimum degree for a left vertex. Let's call that delta min equals minimum degree for left vertex. Okay, and now you can look at the maximum degree of a right vertex, that delta max equals maximum degree for right vertex. And it turns out that if delta min is greater or equal to delta max, okay, so if the minimum degree for a left vertex is at least as large as the maximum degree for a right vertex, delta min is less than or equal to is greater or equal to delta max, then Hall's condition is guaranteed. Okay, and we'll show that. It's an argument that's simple enough for us to show right here on the board. Okay. And if Hall's theorem is guaranteed, then you know there's a matching. And one application of this is to Latin squares. You can see the application as an example in the text. Okay, so proof. So if this is true, then Hall's condition is satisfied. And if Hall's condition is satisfied, you know there's a matching that covers the left vertices, that saturates or completes the left vertices. So let's prove this. So here's the picture. Consider any left subset. So you have a left subset X, okay, and a corresponding, so X has edges, okay, X has edges, okay, boom, 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 who knows, okay, and that goes into some right subset. All those edges combined, when you collect up all those vertices, that's the neighborhood of X. Okay, so X goes into the neighborhood of X. And it's possible that there are other edges going into here. What we know is that all these edges go into there, but there might be other edges going into here. So I'll put those as dotted other edges. There might be other edges. Okay. Now, let's look at the number of solid edges, the ones coming out of X. The sum of the degrees of the vertices in X, okay, must equal the number of those solid black edges coming out of X. So sum for I, for the vertices I in X, so the vertices I in X, so the sum of those degrees, okay, equals the solid black edges, leaving, that equals the number of solid black edges leaving X. Okay. And all of those edges going to N of X, but there might be more edges coming into N of X. So that's at most the number of edges going into n of x. Because there might be other edges coming in, but those edges are not coming from x. Okay? And so this, the total number of edges coming into n of x is exactly the sum of the degrees, because each of those edges contributes 1 to a degree in n of x. So this is exactly the sum of the degrees for all vertices j that are in n of x. It's the sum of their degrees, delta j. Okay. But now this here is at least the size of x times delta min. Because each degree is at least delta min, so the sum of the degrees is at least delta min times the size of x. And this is at most the size of n of x times delta max. Because delta max is the maximum possible value for that degree. Okay. And so if I compare, I see that the size of x delta min is at most the size of n of x delta max, which means that size of x is at most the size of n of x times delta max over delta min. Okay, but delta max over delta min is less equal to 1 because delta max is less equal to delta min. So this is less equal to 1, so this is less equal to n of x. Okay, so let's see what we have proved. We have proved that if the minimum left degree is at least as large as the maximum right degree, then for any subset x, the size of x is at most the size of the neighborhood. And we didn't make any assumptions about which subset you pick. So this holds. The size of x is at most the size of the neighborhood of that subset for any subset x. This means that Hall's condition is satisfied. Hall's theorem says that if Hall's condition is satisfied, there must be a matching which covers all the left vertices, which uses all the left vertices and assigns them uniquely to right vertices. That's the proof. And this is a much more convenient condition to use than Hall's condition. Okay, and you can see the example application to Latin squares in the text. Okay, so what's a Latin square? A Latin square, for example, is, so here's a Latin square. Okay, 1, 2, 3. So this is a 3 by 3 Latin square. 1, 2, 3, 2, 3, 1, 3, 1, 2. So what's going on here? If you look in any row or any column, so in this row, 1, 2, 3 appears. In this column, 1, 2, 3 appears. In this row, 1, 2, 3 appears, and so on. So in every row and every column, it's the case that 1, 2, 3 appears. Okay? And can you generalize this to 1, 2 up to n? So that's called a Latin square. And Latin squares have all kinds of uses, and we can use this version of Hall's theorem or this corollary to Hall's theorem to show that we can always construct Latin squares no matter how big the square. Okay? And you can see that application in the text. We'll move forward. Okay, so the topic you've all been waiting for, the mathematics of dating or stable marriage. Okay, and the scenario is, the usual bipartite graph. So you've got Alice, Barb, and Carla who are interested in dating Xavier, Yariv, and Zach. Okay, so boys, girls. And let's look at this very simplified scenario. And in principle, everyone could date everyone else. Okay, so there are potential links, there are potential edges, from everyone on the left to everyone on the right. And at the end of the day, we need to set up a set of marriages or we partner people up together, let's say for life. Okay, and let's imagine that we have picked, X with A, Y with B, okay, and Z with C. So any matching would do. Okay, so we have picked the marriages X to A, Y to B, and Z to C. Okay, so what's different between what we did with tasks and resources? What's different is now we're going to add a new ingredient, which is preferences. So before tasks couldn't care less which resource performed them. Okay, but now people care about who they date. So people have preferences. And one way to represent preferences is using what's called preference lists. So our boys and our girls, they have preference lists. So X likes A, then B, then C, in that order. Similarly, everyone has a preference list. Y likes A, then C, then B. Z likes B, then A, then C. And similarly, A likes Z, then Y, then X. B likes Y, then X, then Z. C likes Z, then X, then Y. Okay, so everyone has a preference list. Now in practice, nobody publishes their preference list. Malik doesn't go out to the world and say, okay, among all you 10,000 people, this is the order in which I prefer, and then let's go and make stable marriages. No, everyone has their preference list. I'm listing them just so that we can see what's going on. Okay, in particular, what I want to highlight is the pair of marriages, X to A and Y to B. Okay, now why am I highlighting this? Because, okay, X and A are married, so they're holding hands and walking down the street. Okay, and then Y and B are married, and they're holding hands and walking down the street, that same street. Okay, and Y looks at A and says, I'm married to B, so Y is married to B, but wow, does Y prefer A to B much more? Okay, so Y would prefer to be attached to A. Okay, and does A reciprocate? So A is walking down the street with X and notices Y and looks at her preference list and says, you know what, X, I don't really like X. Why am I hooked up with X? Look, there's Y over there, and I prefer Y to X. So I prefer X. A would prefer to be with Y. Now this is the potential for an explosion. Okay? Because look, A and Y both prefer each other to their current partners. Okay? A and Y prefer each other to their current partners. That's asking for an explosion. We call this a volatile pair. Volatile pair of marriages. And what's going to happen here is this is a very unstable situation. X and A are going to explode, Y and B are going to explode, and X and A are going to hook up. And let's look at what happens to X. Well, X much prefers, A to B, for example. That would leave X and B unpaired, so maybe they can pair up. But X would much rather be with A, okay? And B would much rather be with Y. Okay, B prefers Y to X, but that's irrelevant. They're not the decision makers in this explosion. It's that, all you need is one volatile pair who prefers to be with each other rather than their current partners, and you've got an explosion. Okay, so when we assign the marriages, to have a stable society, we would certainly like there to be no volatile pair. So the marriages are what we call stable. So we want no volatile pairs. Okay, so this assignment of X to A and Y to B and Z to C is not stable. It's not viable. Okay. Now, interestingly, in society, we would certainly like to have a set of stable marriages. So you might think, we have a dating algorithm, then we all go out, we date, we get married, and so on and so forth. Okay. Does that dating algorithm result in stable marriages? Okay. Well, I don't know, but I'm going to show you an algorithm that can accomplish that can accomplish stable marriages. It's a very simple algorithm, and it doesn't even need to know the lists of everyone ahead of time. So everyone just knows their own list and makes decisions for themselves. Okay, and this is an algorithm that is very similar to like dating that occurred 500 years ago in the time of Shakespeare, and when men wooed women. Okay. So I'm going to show you this dating ritual. We'll call it a ritual because I don't know if it still exists today. Okay, and in this dating ritual, you've got balconies. Okay, and this is my attempt to draw balconies. You've got some balconies, and some people are standing on the balconies. So let's assume that the women are standing on the balconies, because that's how it happened 500 years ago. Well, the women would stand on the balconies, A, B, and C. Okay. And then on the terrace below, the men would come and read poetry and woo them. Okay, so what we're going to do is we're going to play the dating game where men are going to woo women who are standing on balconies, okay, and see what happens. Okay, so let's call this the dating ritual. The dating ritual. Okay, and what are the men going to do? Well, every man is going to be somewhat rational. The women are on balconies, so I'm going to pick a woman to woo. So on day one, okay, each man picks a woman who they're going to woo. Okay. And what's the natural thing to do? Each man consults their list of preferences and clearly is going to go for the top choice. Okay, so this actually leads to a little bit of a problem because X and Y will both go and try to woo A. Okay, so X and Y are both there trying to woo A. Maybe they get into a fight or something, who knows? But let's assume they read poetry. Okay. And then Z goes and woos B. So Z is wooing B. And what happens to C? C is all alone on the balcony. Might as well just go and do Fox homework or something. Okay. So C is all alone on day one. Poor C. No wooing going on for C. Okay. Now the interesting thing happens at the time of the wooing. So B has got a single suitor, but A has two suitors. So A is going to do the rational thing, right? A is going to tell, one of these guys, bye-bye. Okay. And so let's see what A will do. So A has a choice between X and Y. Okay. And so clearly A prefers Y. So A says bye-bye to X. Bye-bye, X. X is gone. X has been told, you're no longer needed here. Okay. So, X, angry as hell, never to be seen near A again, completely wipes A from his, memory and RAM and USB and social media and everything. Completely wipes out A from his mind, from his history. So he just wipes A out. A no longer exists. A is dead to X. Okay. Now, another interesting thing comes. When we think about what should A do with Y, what should B do with Z. The obvious thing to say is, hey, let's get married. No, don't be so rash. Don't be so quick. Be patient. Here's the game that A and B play. A says to Y, you know what? I like you. Come back tomorrow. You may be the one. That's a very different scenario to you are the one. Okay, so definitely A has rejected X, but doesn't necessarily accept Y. You may be the one. I like you. Let's come back tomorrow. And the same game is played by B. You know what? I like you. Why don't you come back tomorrow? Okay. So day 2 comes, and diligently Y comes back and Z comes back because they're A and B are respectively at the top of their lists. What does X do? Well, A is dead to X. Okay? So A looks at his list and says, you know what? I'm going to go and woo B because B is my next choice. So X pops up here to the dismay of Z. Okay? Because, we get the picture. C loves Fox. And C is always doing Fox homework. Nobody to woo C. Okay, but why is this to the dismay of Z? Because now, A doesn't have a choice anymore, but B has a choice. Okay? B looks at X and Z. B looks at X and Z. You know what? I prefer X. So Barb says, bye-bye, Z. Bye-bye, Z. Okay, and Z, angry as all hell, wipes his hard drive clean of B. Social media, everything done. Okay, B is dead to Z. Okay, and same game. A tells what? I like you. Come back. We may be the match. And B says to X, I like you. Come back. We may be the match. Okay, and so diligently on day 3, Y comes back, X comes back, and C looks at the balcony but is starting to get the picture. Okay, Y comes back, X comes back. But what does Z do? Well, Z goes back to his list and picks A, who's now the current winner on his list. So Z picks A. Oh my goodness. Now we've got another competition between Z and Y. Okay, and who gets to choose? In this case, A gets to choose. And A looks at Z and Y, and now you see the patience of A has been rewarded because her top choice has come along. So bye-bye, Y. Okay, and Y, A, you are dead to me. Okay, and again, they play the same game. A says to Z, come back, you may be the one. Although A could, in fact, say, yes, let's get married, because A knows that nothing better is possible. But, we'll just play along. Come back, Z. You can date me a little more. And B says to X, come back. And, C is still doing the Fox homework, and day 4 comes along. 4 comes along, and Z diligently comes back, and X diligently comes back. And let's see, what does Y do? So Y looks back at his list, and now the current best is C. And so finally, C gets her first date. Okay. And now you see the situation is never going to change, right? Because they will just each say, come back to their corresponding suitors, and we're done. We've hit an equilibrium. And so we found the set of marriages, okay, A to Z, B to X, and C to Y. Okay, so couple of things. The first thing is that this dating ritual should look eerily similar to what goes on today in the dating circles and what went on 500 years ago and what has been going on for, millennia. This is the way boys date girls. Okay, and you might wonder, well, so one thing that you should take away from this is if that you're the girl, don't immediately catch on to the first thing that comes by. Tell them to come back. Tell them to come back. Tell them they may be the one. Let's date a little. Come back. Okay, so that's the first interesting thing that pops out of this algorithm. Okay, and the second interesting thing that pops out of the algorithm is, look, it ended. Okay, and it ended with every girl and boy matched. So nobody's left out in the end. And indeed, C would have ultimately gotten a match. Okay, so, observations. 1. The algorithm ended. Okay, and indeed, if there are n boys and n girls, one can show that, the number of days it takes for the algorithm to end is no more than n squared. So, O of n squared steps. Okay. And one way to see that is that at every step, at least one boy, if you're not already at equilibrium, at least one boy will cross off one girl from a list. And since the number of entries in this list is n squared, the algorithm cannot go on for more than n squared. And step 2, second observation, everybody gets matched. So no boy is left without a girl, and no girl is left without a boy. Well, if no boy is left without a girl, and girls are matched to at most one boy, then, since there are an equal number of both, both boys and girls are all, given matches. Okay. And, this is a very eerily, familiar algorithm. It's what's going on. And you might wonder, well, how did this evolve? Probably it evolved because it encourages stability in the society. Something must be right about this algorithm for this algorithm to have withstood the test of time. And indeed, it is possible to show that there are no volatile pairs in the resulting set of matches. There are no volatile pairs. In other words, the marriages are stable. Very interesting. So this dating ritual that has withstood the test of time is guaranteed to produce matches which are stable. Okay? The marriages that are produced have no volatile pairs. So there's no potential for scandal if this algorithm is faithfully followed. Okay? So this is the content of a theorem. You can see the theorem in the book. It's the Gayle-Shapley theorem. Okay, and we more or less we can sort of the hard thing to prove is that there are no volatile pairs. And okay, so you can see the book for how to prove that. But there's one more interesting thing. Okay. It looks like the girls are in charge. It looks great that they're on top of the balconies, waiting to pass judgment on their suitors who come along like little mice. Okay. And when the mice come, they pick, they tell some to disappear, and they tell others to come back. So it looks like they have all the power. So the girls have all the power. Okay. But that's deceptive. Just because they have the power, they're the ones who look like they're the ones making the choices. They are the ones who lose. They get shortchanged. The girls get shortchanged. And what does that mean? So, it turns out that there are many ways to do stable marriage. There can be many ways to do stable marriage. And among all the possible stable marriages, so they get shortchanged, what that means is among all possible stable marriages. Okay. The one that is produced here, okay, is the worst for the girls. So every girl is worse off. They cannot be more worse off in any other stable marriage. So this is the worst for the girls. But how is that possible? They have all the choice. Okay, they're the ones making the decisions. They have the power. In fact, and the opposite is true for the boys. Okay, among all the possible stable marriages, this is the best possible outcome for the boys. There's no other stable marriage in which any boy can be happier. So the boys got the best possible stable marriage, and the girls got the worst possible stable marriage. And what does that have to do with? That has to do with the fact that it's the boys who are wooing the girls. So it looks like the girls have power, but indirectly, it's actually the boys who have power. So while the girls seem to be making the decision, before the girls get to make decisions, it's the boys who make a decision. So they go one by one through their list, starting from the top. Okay, so they get to, and if their top works out, they got their top. If their top doesn't work out, they were never going to get their top. And so they go down to the next and then to the next. So they move through their list from best to worst, and where they end up is where they end up, and it's the best that they could have possibly accomplished. Okay. Well, the girls, meanwhile, actually, even though it looks like they have all the power, they're at the mercy of the boys. Because, they get to decide, but they get to decide only over whatever shows up on their doorstep, like C. C only gets to choose between whatever shows up at her doorstep, and Y showed up, and that's all I have. Okay? And so, even though you're making the choice, you're making the decision, you have to decide among usually the bad alternatives. For example, in the case of C, perhaps. Okay? And that's what's going on. Even though they make the decision, surreptitiously, the boys are making the first decision of who to woo. So they're going through their list from top to bottom. Okay, so what's the lesson? And you learned it here in Fox. It's a discrete math lesson. In this dating ritual, it's better to be the person wooing than the person being wooed. So, if you're engaging in this dating ritual, make the first step. You're the one who should be the one asking out. Whoever you are, whether you're the girl or the boy, make the first step. That's when you get the best outcome. Because you get to implement your list, not wait for whatever shows up and make a decision. You heard it here first. Okay, so let's erase, and we're going to come back and talk about coloring. That's another big ticket item. Bam! Okay, so let's talk about graph coloring. And, it's a problem, a task that we like to solve on graphs that even a 3-year-old could understand. And I'm going to present it to you in two very different contexts. Okay, so, imagine that you have a bunch of radio stations, R1, R2, R3, R4, R5, R6, and I'm going to show you now, what's the radius, what's their reach. Okay. So they each have different reaches. Okay, so R3. So this is R1's reach. Okay, this is R3's reach. This is R2's reach. Okay, and then R5 has a certain reach. Okay, R4 has a certain reach. Okay, and then R6 has a certain reach. Okay, and what's interesting about, so the radio stations broadcast at a particular frequency. That's their frequency band. And let's consider, a reader, a listener, for example, in this region. Okay, so a listener in this region can hear both R1 and R3. And so, if they both broadcast at the same frequency, this listener will hear garbage. Okay, and similarly, a listener in this region here, this region, that's the intersection of the 3 regions of reach. So this listener can hear R1, R2, and R3. Okay, and so that means that if any one of them is broadcasting at the same frequency, then that listener will hear garbage. And same thing here. So this is a region of intersection. Basically, where 2 regions intersect, the corresponding radio stations must be using different frequencies. Okay. And so the question is, what's the smallest number of frequencies we need in order for all the radio stations to be able to broadcast to all the listeners? And we could easily just assign each radio station its own frequency, but then that's using up a lot of the bandwidth that's available, and the FCC, auctions bandwidth for a very high price. So you don't want to use that many frequencies if you don't have to. Okay? Totally different problem. So you have Alice, Bob, Charlie, David, Erin, Fiona, and Gavin. Okay, so they are all taking courses. Okay, and we have courses C1, CS1, C2, Calc 1, C3, Psych, C4, CS2, C5, Calc 2, and C6, Fox. So they're taking courses. Okay, all a bunch of different courses taken by a bunch of different people. So this is a bipartite graph. We saw this in matching. Okay, and I'm going to tell you who's taking what courses by providing the links from the people to the courses. So Alice is taking course 1 and course 2. Bob is taking course 1 and course 3. Course 1 and course 3. Charlie is taking course 2 and course 3. Course 2 and course 3. David is taking course 2 and course 4. Course 2 and course 4. Erin is taking course 4 and course 6. 4 and 6. Fiona is taking 5 and 6. 5 and 6. And Gavin is taking 3 and 5. 3 and 5. Okay. So now what's going on here? What's going on here is that, at the end of the semester, we have to assign final exams to the courses. And what we know for sure is that, for example, course 3 and course 5, which are both taken by Gavin, they cannot have the same final exam schedule. Okay, because if they do, then Gavin cannot take one of the finals. So any two courses, if they share a student, if they have the same student, cannot have the same final exam. So, how do we assign final exams, final exam times, and how many final exam times do we need to assign? And, we could certainly just assign a different final exam time to each course, and then we'll need 6 final exam times. But imagine, at a school, a reasonably large school, where you have something like 500 courses, you can't just assign 500 3-hour slots. We'll be taking exams till the end of the summer. Okay. So, what's the minimum? The minimum number of frequencies needed. What's the minimum number of exam times needed. Okay. Now, here we already started with a graph, and we're going to massage it into a different graph. Here we have just a bunch of regions occupied by, broadcast to by a bunch of radio stations. So, the thing that comes to mind is, when two regions overlap, that introduces a relationship between radio stations. Okay, so for example, R1 is related to R3. So let's draw a graph where we have R1, R2, the radio stations, R3, R4, R5, R6. Okay. Now, this general kind of problem, so here we're trying to resolve the conflicts in between radio stations by giving them different frequencies. Here we're trying to resolve the conflicts between courses by giving them different exam times. Okay, and so while these problems look very different, the challenges that we face both involve resolving conflicts. And so what I'm about to do is a general approach to resolving conflicts. You construct a conflict graph. So who conflicts with who? So we have our radio stations. R1 conflicts with R3. R1 conflicts with R2. R2 conflicts with R3. Okay. Then R2 conflicts with R4. Okay. R3 with R5. Okay. And R4 with R6. And R6 with R5. Okay. So that's the conflict graph. Interesting. Let's see what the conflict graph here looks like. And we're going to do the conflict graph for courses, because they're the ones that potentially conflict. So we have, courses C1, C2, C3. So we'll put them as C1, C2, C3, C4, C5, C6. Okay, and now Alice introduces a conflict between C1 and C2. So C1 and C2 conflict. Bob B introduces a conflict between C1 and C3. So C1 and 3C. C between C2 and C3. Okay, D between C2 and C4. Okay, E between C4 and C6. Okay, F between C5 and C6. And G between C3 and C5. Oh, look! Even though these are totally different problem settings and they came from different places, they have the same conflict graph. Okay, now how are we going to resolve conflicts? We need to assign different radio stations to any two radio frequencies to any two radio stations that conflict, i.e. that have an edge. We need to assign different exam times to any two courses that conflict, i.e. that have an edge. Very similar problems. Okay. Now, let's formulate this in an abstract way. Let us represent by, radio frequencies. Let us represent radio frequencies with colors. Okay. So, if I give this radio station the red frequency, then I cannot give the red frequency to either of those. Okay, so I can maybe give this radio station the green frequency. Okay, and now that I've given this green, since this has an edge to both of these guys, I cannot give red or green to this guy. So let me give this guy the blue frequency. Okay, now since I'm trying to minimize the number of radio frequencies, well, I can reuse my red frequency here. So I can reuse red here. Okay, that means I cannot use red here. Okay, and I cannot use green here, so I can reuse my blue here. Okay, and that means that if I don't want to start a new frequency, I'm going to have to use green here. Okay, so I can get away with 3 frequencies, and I cannot get away with fewer than 3 frequencies because all these guys interfere with each other, and so they need 3 frequencies. Similar thing goes on here. If I let the color not represent the radio frequency, but the exam time. So this course gets the red exam time. This course gets the red exam time. Okay. This course gets the blue exam time. This course gets the blue exam time. And this course gets the green exam time. And this course gets the green exam time. Then I see that with just 3 exam times, I'm able to satisfy, giving all the exams so that all students can take all the exams. Okay. Now, what you'll see that both of these problems reduced to, what explicitly I solved as a coloring of a graph problem. That is all that graph coloring is. So simple. I give you a graph and I ask you, can you color the vertices? So graph coloring, can you color the vertices so that if 2 vertices are connected by an edge, so if 2 vertices are neighbors of each other, they must get different colors. So that's just a very abstract coloring problem. Can we do it? And if we can do it, then we can solve this problem and we can solve this problem. Okay, so that's just graph coloring in general. Graph coloring. So let's talk about graph coloring. Okay, so graph coloring. Graph coloring problem. And now we can formally specify it. I have just described it here. Given a graph G, which consists of a vertex set, which is, V1, V2, up to Vk, and an edge set, which is a bunch of edges, E1, E2, up to Ek, let's call it N vertices and M edges. Okay, color the vertices. Now, of course, it's nice to have, visual colors, but, mathematically we can label each color by a number. So red is 1, blue is 2, and green is 3. So we can just number the colors. Okay, so define colors. 1, 2, 3, 4, and so on. Okay, now color the vertices. That means assign a color to each vertex. So each vertex gets a color. Let's call it C sub I for vertex V sub I, and C sub I is a number. Okay, and we'll assume that you try to use the colors, the smallest indexed colors. So you try to use the colors 1, 2, 3 up to K. Use colors 1, 2, 3 up to K such that if 2 vertices share an edge, such that for every edge, the the two vertices have different colors. So each edge is defined by two vertices, and you want those two vertices to have different colors. And if you can do this with k colors, we say that you have a valid k coloring of the graph. If you can do this with k colors, then you have a valid k coloring of the graph G. Okay, so that's it. I mean, I've just put in sort of a more mathematical form the task that I showed you visually here. Color the vertices so that, for every edge, the two corresponding vertices of that edge have a different color. Okay. Now, in this small example, we did it, we did it visually. So let's try to think of a general algorithm that can solve this problem. Okay, and I'm going to call this algorithm the greedy algorithm, and I will show you the way it works. Okay, so let's consider a graph. Okay, so I'm going to show you a graph. So let's pull up a graph. Okay, and I'm going to label the vertices. So here's V1. Here is V2. Here is V3. Here is V4. Here is V5. So V5. And here is V6. Okay, and I'll draw the graph a second time. V1, V2, V3, V4, V5, V6. Okay. And well, those are just the vertices. Now let me tell you what are the edges. Okay, so this guy's connected to those guys. This guy's connected to those guys, and this guy's connected to those guys. Okay. I'll draw it. I've drawn it twice, just to illustrate something interesting. Okay, so same graph drawn twice. So now what I'm going to describe for you is what's called the greedy coloring strategy. So greedy. Okay. So let's number our colors. So our colors are 1, 2, 3, 4, and so on. Okay, and because we do actually have colors, let's call the first color blue. Okay, the second color red. The third color green. Well, actually they're just numbers, but we can call them blue, red, green, and let's say black. Okay. Now the greedy algorithm works as follows. Okay, we start from vertex V1 and then we go V2, V3, and so on. So we increase the vertices. And whenever it's time to color a vertex, color that vertex with the cheapest, the smallest, i.e. the smallest number color that you can. So when we start with V1, nothing else is, you'll see how this works. So I can color V1 with blue. That's the smallest number color that I can. Okay, good. So I've colored V1 with blue. Now I come to V2. So what color can I give V2? Well, I can give V2 also blue. Okay, because it has no neighbors that are currently colored. So V2 I can give blue. Okay. Now let's talk about V3. Well, V3 cannot get the color blue because it's got a neighbor that's already colored blue. So the smallest color that V3 can get is red. So we give it red. Okay. Now we come to V4. V4 also cannot get the color blue. Okay, because V4 is got a neighbor who's colored blue. So the smallest color that V4 can get is also red. So this is red. Okay. But now this is interesting. Now when I come to V5, V5 cannot get blue. It cannot get red because it's got a blue neighbor and a red neighbor. But it can get green. So we can color this guy green. Okay. And now that we've colored this guy green, we've done V5. Now we come to V6. V6 cannot get blue, cannot get red, cannot get green, cannot get blue, red, or green. So the smallest color it can get is black. And there you have it. Okay, there you have it. A coloring, and we used 4 colors. 4 colors. So this notion of giving the smallest color to a vertex and is what makes this algorithm greedy. And as you can see, we have a valid coloring, because at every step when we color a vertex, we always give it a color that doesn't conflict with any previously colored vertex. Okay, so it guarantees that the coloring is valid. But is it optimal? Nowhere close. Okay, we used 4 colors, okay, to get a valid coloring. I claim you can do it with just 2 colors. Here, I'm going to give this guy blue, and this guy blue, okay, and then I'm going to give these guys red, and red, okay, and now I've done it with just 2 colors. Okay. So the problem with greedy is that, it may use more colors than necessary. It always guarantees that you get a valid coloring. And then you might think, why did we choose greedy? Why did we do that? Because we don't know of an algorithm that can efficiently color with the minimum number of colors. So we don't know how to efficiently color with the main number of colors. So such a simple problem that even a 3-year-old could understand it. I could give them this graph and say, go color, and they'll easily come up with a way to color it with two colors. Okay, I can give it to a 3-year-old, a 5-year-old, a 6-year-old, whatever you want. But if I give this problem in its general form to a mature 25-year-old, we cannot do it efficiently. Bam! And we see that in order to resolve conflicts, we need to be able to color. So it's an important algorithmic challenge that involves graphs. Okay. Let me show you that trees can always be 2-colored. By the way, from this algorithm, you can see that, whenever it's time to color a vertex, at most all its neighbors have been colored. Okay, and so that if it has degree delta, then delta colors have been used, and so you'll never have to color a vertex with a color higher than its degree +1. Okay, so this algorithm shows that you will never color a vertex with a color larger than degree +1. So that means that it's always possible to get a valid coloring of a graph with a number of colors that's equal to the maximum degree +1. That's always possible. And that coloring is easy to do with greedy. Okay, but how to get the minimum number of colors, we don't know. Okay, let me show you that trees, and in general, but I'll just show it for rooted binary trees, can always be 2-colored. Rooted binary trees are 2-colorable. Okay, and the base case is trivial with the epsilon. So I'm going to use structural induction, and the basic idea here is that I just need to show that if the parents are 2-colorable, then the constructor rule preserves that the child is 2-colorable. That's structural induction. So let's take 2 parents, okay, and let us assume that they're both 2-colorable. Okay, so for the root, so 2-colorable means that you have given, let's say, 2 colors to the vertices, let's say red and blue. So let's assume that this guy got blue, okay, for the first vertex, and then whatever inside, maybe there's some blues and some reds, but any blue is not connected to another blue. So maybe this is connected to a red up here, and so on. Okay, now we can connect this guy, and then maybe red, and then so on. So we've got a tree here, and we've colored the root blue. Okay, now supposing we've also 2-colored this tree, which is assumed because they're both going to be parents. Okay? So, what could happen is that we've colored this root red, okay, and then, maybe blue here, and then red here, and so on. Okay, so these are the links, okay, and so on. Okay. Now, I would like it instead to be the case that I've colored this guy with blue up there. And can I be always sure of that? Yes, because I can just relabel the colors, flip the colors. Wherever I use red, use blue, and wherever I use blue, use red. So here I can make this blue, and this blue, and I can make these red. Okay, I can just flip the colors. In doing this, I can always ensure that these two roots have been colored the same color, and these two parents are two colorable with the roots being the same color. Okay, so remember where I'm going. I've assumed that the parents are two colorable. I want to show that the constructor preserves two colorability. Okay, so here I've got a two coloring of the parent with a blue root, and I'm going to request that whatever coloring you give me for the second parent also must have a blue root. And I know it's two colorable, and if you need red here, then let me flip the colors and get blue here. Okay, but now what does the constructor do? The constructor takes these two roots, okay, and connects them to a new root. I claim that this tree is two colorable, and here's the proof. I'm just going to color this red. Bam! I've colored the child that was produced, because look, this child red is connected only to blue nodes, and then these two were two colorable, so I haven't changed anything in there. And so these are valid two colorings of the parents, and with this guy being red, with this vertex being red, I've got a two coloring of the child. So, the constructor for RBT preserves two colorability. And that's all I need to prove for the structural induction, in addition to the base cases, but the base cases are easy to verify. Okay. So I just proved that if the parents are two colorable, then the child is two colorable. Therefore, every RBT is two colorable. And effectively, you can see this as follows. So here is an RBT. Okay. Basically, what's going on is an RBT has levels, and effectively, I'm coloring every other level one color, and every, in between level, the other color. And now you can easily verify that this is a valid coloring. No edge connects two nodes, two vertices of the same color. Okay, so that's coloring. Very important for conflict resolution. Trees can be two colored, and there's an efficient greedy algorithm that gets you a coloring that uses at most the maximum degree plus one colors. And we use coloring a lot for conflict resolution. Let me show you a whirlwind tour of other graph problems. Other graph problems. Okay, so let's talk about lots of different forms of graph problems. Okay, so we'll start with connected components. Components. Okay, so you have a bunch of people in a social network, okay, and and they're friends with each other in certain ways, okay, and you have a bunch of products that you can give away for free, and when you give a product to a friend, the friends of that friend will pick it up, and then the friends of those friends, and so it'll spread along these friend links. So who should you give the product to? So in this problem, what you can do is you can identify this group, give one to this guy, then it'll spread. One to someone in this group, identify this group, give one to someone in this group, and it'll spread. And what we have identified here are what are called the connected components. Within a connected component, everyone's connected to everyone else. Okay. So this problem, it turns out we have an efficient algorithm to solve. It's easy. Okay. Let's look at another problem that's also easy. Okay. So, every year there's a day in Troy where I work, which will have something like 3 feet of snow. So, you've got a road network with points of interest, okay, that defines a road network. Okay, and let's say, one of these roads, one of these points of interest is the depot, the depot which stores the snowplows. Okay, so what's going to happen? Someone's going to come, get in the snowplow, and drive along each road, plowing as they go along. But they don't want to drive along the same road twice. So the question is, can they hit every road? Can they drive along every road exactly once and come back to the base? Okay. And we saw this problem before. It's the same problem essentially as Euler's Königsberg's bridge problem, where he had to traverse the bridges without repeating a bridge. Okay, and we know how to solve this problem quickly. We can determine whether it can be done and find the tour for the snowplow efficiently. Okay, so this is an easy problem. This is called an Euler cycle. Okay. Now, if I tweak this problem a little, it's not the snowplow that needs to hit every edge, but it's a salesperson at their base that needs to hit every vertex. So every vertex is a client and come back home. Okay. So that's called a Hamiltonian cycle, where you need to hit every vertex exactly once. A variant of that is the salesperson needs to hit every vertex once, or maybe more than once. He needs to hit every vertex while minimizing the distance traveled. That's called the traveling salesperson. Okay, so in the Euler cycle version, you have to traverse every edge exactly once. In the Hamiltonian cycle of traveling salesperson, it's not that you have to hit every edge exactly once, you have to hit every vertex exactly once. A small change to the problem. These problems are very hard. We don't know how to determine a good way to visit every vertex and return, or even if it can be done. So these problems are very hard. Okay, let's consider another easy problem. Network flow. Okay, so network flow, where you have you, the source, okay, and you have a destination that's called a D, and there's a network of ISPs in between you and your destination. Okay, and they're connected in certain ways, and and each of these links between two that forms a connection between, let's say, ISPs has a bandwidth, and you'd like to figure out what's the maximum rate at which you can send packets from you to your destination, obeying the bandwidth constraints, and also obeying another constraint, which is that packets cannot be dropped. So if you send packets here, they must either leave this way or that way, or some combination of that. Packets cannot be dropped. So what's the maximum flow that you can get from the source to the destination? That's called max flow, and this problem is easy. Easy means we have efficient polynomial time algorithms to solve. Okay. Whereas hard just means that we don't know of any efficient algorithms. If you can find an efficient algorithm for a problem like that, bam, you're famous. Okay, let's consider another easy problem. Okay, so it's similar to this problem here, where the task now is to convert some of these roads into highways. Okay, and each road has a certain cost to become a highway, and you need that all points of interest must be connected via highways. So here's an example. So I might start by connecting these guys by highways and this guy, okay, and then I might then connect these two by a highway, and then this guy and that guy, and then that guy and that guy. And now you see every pair of vertices can be reached using only highways. And what you'll see here is I've drawn a tree. If you imagine this guy as the root, I've drawn a tree, children, and this node has a child here, and that node has two children, and this node has a child. So I've drawn a tree. So I've effectively constructed a tree from some of the edges. And I'd like to construct a tree where after I build these roads, it costs me the minimum amount of money. Okay, so that's called a minimum spanning tree. Find me a highway system that costs me the minimum to build, but uses some of the roads and makes sure that everyone is connected. That's called minimum spanning tree. Minimum spanning tree. Tree because you see I've constructed a tree. Spanning because every vertex can reach every other vertex, and minimum because I want it to cost the smallest amount. Okay, this problem is easy. Okay, now let's discuss some hard problems. So again, think of a network. Okay, boom, 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 boom. Okay, road network, for example, connecting points of interest. Okay, and your task is to place policemen at points of interest so that every road can be monitored, can be surveilled. Okay, and you can think if I place a policeman at a particular intersection here, that policeman can surveil, can watch, the roads that are coming in to that point of interest. And so the question becomes, what's the minimum number of policemen you need to watch all the roads? Okay, so min number of policemen to watch all roads. That we call the vertex cover problem. So the policemen cover the roads, cover the edges. So that's called vertex cover, and that's hard. Okay. We don't know an efficient way to solve the problem. Let's change the problem a little bit. It's not that you have to cover the roads, but you have to service vertices. So imagine that we're placing now not policemen, but we are placing hospitals. Okay. So now this hospital that we have placed, okay, covers, we'll say, dominates this vertex, this vertex, this vertex, and this vertex. Okay, let me put them in red. So red, 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 red. It dominates those red vertices. What does that mean? That means that in case of an emergency, if you're at one of those red vertices, you don't have to travel more than one hop to get to a hospital. Okay, but I would like that to be the case for all the points of intersection, so that nobody in the case of an emergency needs to travel more than one hop. How many hospitals do you need? Okay, how many hospitals do you need? Okay, so the number of hospitals. So no one drives too far to a hospital. This problem is called dominating set, and it is hard. We don't know how many hospitals you need, let alone where to put them. Okay. And last problem, you're not putting hospitals, but you are putting McDonald's. Okay. So imagine I give you a budget of 2 McDonald's. So you place 1 McDonald's here, and you place 1 McDonald's here. Okay. And so now you ask, how far does a person need to travel in order to reach a McDonald's? Okay, so imagine that I had another person here, let's say. Okay, now this person has to travel 1, 2, 3 hops to reach this McDonald's. Okay. And we say that person is the worst off in this network with respect to how the McDonald's are placed. So you may ask, well, I've got a budget of 2 McDonald's. Where should I place them so that nobody has to travel too far to reach a McDonald's? Okay. So that's called facility location. Okay, so facility location, i.e. where to locate your facilities. So place your McDonald's so no one has to travel too far to get to one. So you place the McDonald's so that nobody has to travel too far to get to one. McDonald's would love to figure out this problem so that, they make the most money, because people will come more often if they don't have to travel so far. Okay. And so you can see that, there are a lot of problems that I'm showing you here. A lot of problems coming from very diverse areas. And one of the skills of a computer scientist is to be able to take a problem, okay, like, finding out where to put the McDonald's, or where to place the policeman, or where to place the hospital, and massaging it into graph form so that we can use all the algorithms that we know. Now, in some cases, we have efficient algorithms. In some cases, we don't. Okay? But, that's the nature of the game. Okay? So today, we looked at matching, which is relevant when you want to match resources with, let's say, tasks or dating. And matching is everywhere. Match medical residents to medical schools to go and do residencies, and so on and so on. Match liver donors to liver recipients. Okay, matching is everywhere. We need to do it efficiently. We need to do it stably. We need to do it optimally. Coloring is everywhere whenever you need conflict resolution. So that's 2 examples of this task of taking a problem and then massaging it into graph form. Get good at that. Okay? And then you'll be able to solve all kinds of problems. And with that, we're checking out.